the mean cost in one cycle divided by the mean cycle length. That's a renewal reward theorem, if you guys remember. That's this. So y1 is a one random variable characterizing the random cost in one cycle from 0 to t1, and t1 is the length of the first cycle, and this is a function of two expectations. Of course, they're not independent. Make sense? Right? There are many examples though. If you have this technique, if you can deal with this, you can do many things. You can estimate many. You can construct common interval for many things, including variance and covariance and that. An example first. Then we talk about high dimension. Let t be the random failure time of a system. So time until the system crashes or something. Okay. Then 1 over et is referred to as long-run failure intensity rate. Of course, you can argue that why you don't care about E of 1 over t. I mean, this is just a convention. In certain systems, they want to estimate 1 over et rather than E of 1 over t. Let's say this is the objective. Alright, you can see this is a smooth function of et. Reciprocal function, right? Alright. G is 1 over x. How do you estimate t? You run n samples and estimate, you collect the time at which each sample I, on each sample I, the system crashes. So you collect n samples, right? You do what we did in the previous topic n times, right? Like insurance company. The insurance company, the capital falls under 0 and you stop. Then you do it again, Okay. Then you take derivative of g, because the derivative is involved in the plus minus term. That is given by this, right? So take a derivative which is 1 over x squared and negative. Take square 1 over x squared, no problem. So g prime ex squared variance t is variance t over this guy. X is replaced by et, so it's et4. So basically I'm applying the formulas here. This is something appearing in the plus minus term under the square root, remember? We need this, or this. I now compute this too. Okay. I need this, because this one I know, but I need to establish the plus minus term. That's this. So the CLT implies that this guy now converts to a normal random variable with mean this and variance this, and this variance over mean to the 4 is approximated by sine covariance divided by sample mean to the power 4 though. Or you can simply use the formula there and just plug this into the formula. So you can see that it should be this guy over n, take a square root. So you remove the 2, you reduce 4 by 2, and you have a root n here. So this is basically one application of our formula using this specific g. That is 1 over x. This is just an example. Right? You see, it's not entirely obvious, right? Without introducing those theories, how do you know this is what you need to do, right? For the plus minus, right? But it's all supported by CLT, right? Question about this? This is just a concrete example. When we introduce a new method, the first thing I would do is to give an example in a concrete case. Then sometimes we introduce the insight, right? All right. Let's work on high dimension. High dimension. Let's consider 2 dimension first, right? We have seen 2 examples for 2 dimension. This example and this example. Okay? And you can see that 2 dimension, the g is the expectation, g a function of 2 expectations, and the 2 random variables x and y, they may be correlated. Most of the time they are correlated, right? Correlated here, correlated here. Okay? Alright. Let's do this. Our objective is to estimate theta, that is a g function of 2 parameters, 2 expectations, mu x and mu y, allowing for correlation, dependence between x and y. Right. So given mu x stands for ex, mu y stands for ey, and sigma x squared, sigma y squared are the variance and the covariance. Because this covariance may not be 0 now. Monte Carlo estimator will be this, obviously, right? Let's say you are able to generate pairs of x, y. Like you got one pair x1, y1, estimated, generated, using, let's say, calculus. right? We know how to generate correlated random vectors now, not only two dimension. Generate x1, y1, one pair. Generate an IID pair x2, y2, x3, y3, and so on, right? You have IID pairs. Within each pair, you have correlation, right? Then you can average all the x component to get x bar. You can average all the y component to get y bar, and that's your estimator, right? Obviously, right? Because this guy converts to this guy converts to that, and it's large enough. This is it. Now let's talk about the plus minus term, right? Okay. How to build a common interval, right? Theoretical basis is a multi-dimensional CLT. So I'm not gonna prove it, but I'll just briefly explain the intuition of it. You have seen this guy, this component converting to a normal random variable x hat. So this guy converts to a normal random variable with mean 0 and variance sigma x. You have seen this converts to EY. Okay, what if you have a vector of this guy, right? So you have a two-dimensional vector converting to a, n goes to infinity, you have normal here, except that x hat, y hat is a bivariate normal with the mean 0 and the covariance matrix given by the correlation between x and y. So covariance matrix, let me review that. The covariance matrix, the diagonal terms are the variances, and the off-diagonal terms are the covariances. I'm not proving it, but it's very intuitive. One dimension, you don't have to. One dimension would be this guy. Forget about the y. Converts to a normal random variable with the mean 0 and variances. You see that CLT, multi-dimensional CLT, gives you convenient limits that are normal, and also at the same time preserve dependence. And you see, this limiting random vector of two dimension is Gaussian distributed, and the correlation is consistent with initial correlation. That's it. Very intuitive, right? Alright, what are we going to do here? Let's consider Taylor expansion, right? We have done that before, but let's consider, bivariate Taylor extension. So, this bar is close to mu x. This bar is close to mu y. So you're looking for, basically you're in R2 now. So this point is mu x, mu y. This point is off a little bit. Then the difference between the functional value is characterized by the x arrow and the y arrow involving partial derivative. That's Taylor expansion in the two dimension. That's all. Basically, you have a gradient multiplied by the arrows, right? The arrow is vector. So Taylor expansion at this point would give you partial derivative with respect to x times the arrow in x direction, plus partial derivative with respect to y times the y arrow, right? That's actually how we derive partial derivative, plus some little odd term, which will turn, vanish. Make sense? This is just a calculus, right? Second order. So basically, I have a gradient multiplied by, right, partial derivative. Let me multiply by the arrow term, right? This is gradient, right? Okay. All right. So second term, we just put in little o here. Okay. Okay. Let's take a look at. Let's multiply everything by root n here on the left hand side and on the right hand side. Okay. Multiply root n because I know this goes to 0 because this is asymptotically accurate. So I multiply a root n on the left hand side to see whether or not we're gonna have a non-degenerate Gaussian limit. If we have an asymptotic limit which is Gaussian, we're good. We're in good shape. We can build this common interval using the Gaussian properties. All right, let's do this. This guy converts to what? To this, right? So multiply root n to the first term, multiply root n to the second term, and ignore the third term. You have the so-called x hat and y hat appearing in the right hand side. Because why? We got this one converge jointly, so the summation of the two converges to the summation of the two. Therefore, summation of root n times this guy with root n times this guy, that's coefficient of course, we don't care, it's just a constant, goes to the same function, same linear function of the limit. Make sense? Are we okay here, or I should explain more here? Why do we have this convergence here? Is it clear why? So this is what happens. Let me put it on the board. Okay. you see me?
Yeah.
Thank you. So root n x n bar minus mu x, root n y n minus mu y as a vector converts x hat, y hat. Good, right? This is a vector converts to another vector, right? I have a good function of it. It should convert, right? What is my function? My f function is, ax plus by. So my limit, so my x, so this thing converts to f function of the limit, which is, same function, except that ax hat, by hat. That's all. Right? So the a and b correspond to the partial derivative here. Right? I mean, this is just a linear function though. If it's not linear, it's still okay. It's still okay. Right? So we got the first term, right? Okay. What is this guy, right? This guy is a Gaussian random variable. You have x hat Gaussian, y hat Gaussian. You have correlation, so what? It's Gaussian random variable on the right hand side. If you merge the two, the mean is 0 because the mean of this guy is 0, the mean of this guy is 0, the mean is 0. The variance though is equal to the variance of the right hand side, right? So how do you compute the variance of the right hand side? It's equal to the square of this guy times the variance of x plus the square of this guy times the variance of y plus 2 times gx gy times covariance. Right? How do we compute the variance of a plus b, or x plus y, right? Variance of x plus variance of y plus 2 times covariance. Of course, you have some coefficient there. I mean, you have to square them, right? So the sigma square of the right hand side, this whole thing, is just this guy squared times sigma x squared, this guy squared times sigma y squared, plus 2gx gy sigma xy. Simple calculation, right? And that, I mean, you know these things, right? That is this. So you can sort of represent. Right. So you can sort of represent the sigma g here as a gradient times sigma, the sigma matrix times the transpose of this, right? I mean, why do I give you this, right? Because I'm gonna extend this to higher dimension, the same thing. So this formula will be. But looking closer here, I have a CLT now for this new quantity. I have, basically I have a CLT. What is a CLT? Square root of n times my estimator, subtracting the true value. I have a Gaussian variance, a Gaussian limit. Now I'm good to go. I can set up, I can build my confidence interval. Except that I don't know this guy. I'm gonna do my best. Mu x I'll estimate it by the sample mean. Mu y sample mean. Sigma x as x squared. Sigma y as y squared. And the covariance, I mean, this is again, mu is replaced by bar, and this guy is by sxy squared. Do you still remember what is the unbiased estimator to estimate the covariance between x and y? It's very similar to the sample variance, right? Except that it's 1 over n minus 1 summation xi minus x bar times y minus y bar, right? I can estimate this. I don't know what it is. I can estimate this. If you're grouping everything together by exploring each term. So for instance, this guy is 1 over n minus 1 times xi minus mu, xi minus x bar. Plug in all the formulas, right? This is 1 over n minus 1 summation y minus y bar, and this is 1 over n minus 1 summation xi minus x bar times y. Then you combine everything. You take out, you factor out 1 minus n minus 1. You have this simple formula. It's just, this step is just very simple grouping. Okay. So it's just a g partial derivative at the 2 estimator point times the deviation from the center value plus the term for y and square. So that is, this thing, we call that sigma g squared hat, the estimator of the desired variance. So you're going to use this to estimate this. So here comes our CLT though, confidence interval. The 100 times 1 minus alpha percent confidence interval for theta, which is two dimension, is going to be our estimator, right? Plus minus the z square root of the sigma g estimator. Or, I took out the 2 to mean this is the square root divided by 10. Pretty simple, right? Question about this? So as long as you have, whatever you want to estimate, you give an estimator, you can show this guy converts to this guy as n goes to infinity. You can also show that square root of n times this arrow, which is negligible, and as n increases, goes to a Gaussian random variable with mean 0 and variance you can estimate. You build your CLT of this, right? Alright. So this is the case of 2. Then we can consider a general case. Each vector has a k dimension. Similarly, right? Similarly. So each sample is a vector of k dimension, and you allow for correlation among within each k dimension. Before k was 2, right? And you generate n copies here. The n is our simulation budget. The k is the dimension of the vector. Okay. You know that the sample mean of the vector will give you the true value of the mu. Mu is again a vector. The true value vector. You can sort of estimate. You can sort of establish this. Use the k-dimensional CLT to obtain this convergence. Right. This is the generalized version. So this formula is the k-dimensional CLT generalization of what? Of this. This is 2 dimension. That's it. If you have more dimension, it's the same thing, except that right hand side you have k dimension x and y, and you preserve the correlation matrix. Okay. So that extends this to k dimension. That extends that 2 dimension thing. Okay. We do Taylor expansion. We do what we did on the previous page. We're going to see, this is going to be just a gradient. In terms of, the function, you have to look